Biomedical engineering is one of the most interesting fields in the world.
Biomedical engineers try to address all kinds of, I think, exciting questions at the interface of medicine and engineering.
I think I've always been fascinated with the brain and how it works.
One of my best friends became paralyzed when we were 13, and I really wanted to help him walk again.
For me, being a mechanical engineer, the heart was the most similar organ to a pump.
You don't have to be a medical doctor to help save lives.
Biomedical engineering brings these two big fields of medicine and engineering together.
It's a very broad field.
It's the field in engineering that really allows you to make an impact in a very perceivable way when it comes to human life.
Imagine a neurologist 30 years ago without imaging. Their options were very limited. And that's a remarkable example of how engineering can impact medicine very dramatically.
We can think, we can feel, we understand, we interact with others. But on the other hand, we know very little about how brain works. In the field of neuroengineering, we focus on non-invasive brain-computer interface. We put electro sensor on the scalp, and this sensor can pick up extremely weak electrical signal generated by the neurons.
We're able to pick up voltage differences in different areas of the scalp. So when a subject imagines using an arm or a leg, it actually activates the motor cortex in much the same way it would activate if they were actually doing that thing in real life.
And then we decode the signal to try to find out what the subject is thinking or intend to do, and then use that signal to control a device.
The promise of research like this is to allow for paralyzed individuals to interact and to communicate again with the outside world.
We do research in the area of wireless sensors and robotics for rehabilitation. Unfortunately, about 50% of the people that you do any sort of rehab with don't get better, and we really don't understand why.
A major question that we're trying to address is whether through the interaction with a robot, a person can actually learn motor tasks. That's essential in stroke survivors, in traumatic brain injury survivors.
The Locomat is a robotic exoskeleton for robotic gait training.
Let me make you walk a little bit faster now, okay?
Manual gait training, as was usually done, was really strenuous on therapists, where they had to independently move the person's legs through the standard walking pattern.
I want you to think about pulling your knee up nice and high, like you're taking a big giant step.
We've formed a collaboration with the company that develops the Locomat, and so we're actually able to tap in using our own software and change the way that the robot works.
The motion analysis laboratory was established to perform clinical evaluations, mostly in children with cerebral palsy.
Oh, because you guys actually...
We have 8 infrared cameras that go around the room and they point in the central walkway. The cameras emit the light that gets reflected from the markers, and the computer can pick up the movement of the markers. The green lines show the different bony segments, while the yellow line represents the force that is exerted during gait. It's something that will help the doctors in seeing how the outcome of surgeries or intervention lasts through the time. A lot of times when they come in, they want to impress the clinician, so they tend to walk better than what they would do when they're at home.
The shoe that we have developed has sensors that are embedded in the sole of the shoe itself.
Once they put the shoe on, it's like wearing a normal sneaker. You can have monitoring that is less obtrusive, and it's conducted in their home environment, so we can actually collect more data and have a better insight on how the disease progresses.
Wearable technology has become possible over the past 10 years because of major developments that allow us to integrate sensors into garments.
We have the potential that if you can wear some form of a monitoring device, that your vitals can be monitored on a more regular basis, and we can send that information through a cloud environment before you need to go into an emergency department because you're very unwell.
My father is actually an amputee, and when I was young, I promised him I'd make him an arm one day. An amputee can live their life pretty normally with a prosthetic, but the idea that you can just take it to that next level, that's important to me.
One way to do it that we've developed is you could take a plastic scaffold, a polymer scaffold, that could be whatever shape you want, depending on the organ or tissue you're trying to make. Then you might put certain cells on it and give it the right nutrients and also the right mechanical forces, grow it to a certain point, and then do a transplant that onto the patient or into the patient.
If you think about how complex the organ is, it's really difficult to mimic what happens in nature. One of the big challenges is the vascularization. Also, in terms of stem cells, there are a long way to go. We have to understand what makes them differentiate. How can we control them so that they will not develop cancer?
We're working on making various tissues and organs in the body. I mean, new spinal cords, vocal cords, new intestine, heart tissue. So there's a whole range of things that we've been working on. How are the microbubbles doing? Today in the area of drug delivery, some of the things we're most excited about are nanotechnology, where one might be able to deliver drugs right to a tumor or no other place in the body.
Microbubbles, they are very tiny particles, micron size, and instead of being filled with liquid, they're filled with gas. And because of that, they're visible on ultrasound and they're used to improve ultrasound diagnostics. So I'm focusing on trying to incorporate drugs into these microbubbles. If I have those microbubbles loaded with drugs, I can inject them into the body. They will distribute everywhere. But then I can disrupt the microbubbles by an ultrasound beam, and the drug will be delivered specifically where the drug is needed. And so this is the exciting engineering design that I'm working on.
It's not just research that stays on the bench. It's research that goes to the market, goes to help people.
We try to dream up things that we feel can really have a big impact, like maybe a super Band-Aid. We set it up to look very much like a gecko, because the gecko has enormous adhesivity on their feet, so to speak, and the Band-Aid has all these nano protrusions from it. So there's enormous surface area, and so now we're looking at it for making certain forms of surgery easier, like intestinal surgery, various different types of medical adhesive applications. A lot of times what we do is we license things to companies, or a lot of times we've started companies that create products.
There is other cases in which companies are actually coming in and they're asking us to either assess their technology or redesign their technology.
So we get to see cutting-edge technologies, the prototype devices. Major focus of our research is the electrical properties of both skeletal and cardiac muscle. One of the things that we're doing is really novel is we're actually reanimating human hearts. And these are hearts that have been deemed non-viable for transplantation, that were gifts from the organ donors and their families to the lab.
And if they have good enough function, we'll reanimate them and we'll be able to look at the internal anatomy while the isolated heart is functioning.
And just like a heart transplant, you have 4 to 6 hours before you need to reanimate that heart. We'll get it to beat on its own in a native rhythm, and then we can put cameras inside and visualize any of the functional anatomy, really study this device tissue interface of new pacing systems or leads. We actually have a whole free access website that anybody can go online and see the functional anatomy from these human hearts.
Being able to make like an artificial tissue or organ to help someone you love, I mean, that's compelling to anyone, right?
I've been reanimating hearts for the last 14 years, and it's still exciting.
The medical device industry is a consistently booming field. I feel that my job prospects are very good in it.
A large percentage of biomedical engineers actually apply to medical school and go into the health career paths.
I hope to one day be a physician who can kind of be involved in device design and startup entrepreneurial endeavors.
Well, it's a career that just opens all kinds of doors to you.
I think the most important thing as a young student is to get involved early and get involved often. Find research that interests you, because then you'll never work.
Do rotations in different labs at your school to get a feel of what's out there and what would interest you the most.
When I arrived at Minnesota, I looked at 5 or 6 different laboratories and made the decision based on the people working there and the kind of careers the people that graduated from that lab went to.
I started a couple weeks after I became a freshman in college, and it's really paid off for me.
It's essential to know chemistry, to know basic physics, to know basic engineering principles.
The timelines involved here are much longer than in other fields, and that you have to be realistic about that sort of thing.
You have to be passionate about what you do, you have to love your research. When this happens, then you can achieve brilliant results.
I initially joined the Engineering, Medicine, Biology Society to be able to connect with other like-minded people.
That's where I feel that I learned what exciting science is going on in the field.
For a student, an organization like this allows you to connect with people who are well established in their careers, people who can serve as mentors for you as you're developing your career. And more than that, actually get involved with what they're doing.
If you like science, if you like engineering, and if you like medicine, this is just the perfect degree because it combines everything.
If you're passionate about helping people, there's so much to be done as an engineer.